One question we may ask ourselves is that why can a robot build a car but find it difficult to tidy a desk? For example, in manufacturing, we have robots that assemble cars, they paint cars, and they do it in a very efficient way. But when it comes to some other activities, like any activities like our household chores, robots may find it difficult to do or may struggle to do it. And that brings us to the topic of what is easy for robots sometimes is hard for humans. And what is easy for humans is hard for robots at times. So this is a particular popular paradox that we have. And we begin to see this happening also in the field of robotics. It may be easy for a child or toddler to clean up the toys and do all those kind of things and do it safely in an efficient way. But the moment you want a robot to do those kind of tasks, automatically becomes difficult. Then you begin to encounter different kind of issues. Um, the point is in manufacturing, warehousing, logistics, and those kind of industries, traditional robots they fail when confronted with objects they've not seen before. They fail when they are confronted with arbitrary objects. Objects they've not seen before that have very funny shapes. When they're also given some ambiguous instructions that are not clear, that may be clear to human beings, traditional robots also may fail in those kind of scenario. Also, the fact that a robot's work in a particular warehouse or in a particular plant does not mean that when you take it to another environment to do a similar task, it may struggle to do it because it has not received training instruction on how to do that in that kind of environment. And that brings us to the topic of what is currently happening. People call it different names. Some people call it physical AI. Some people call it embodied AI. Some people call it robot learning. But the point that we have now is these days is robots that are able to learn, that are able to do tasks for us the same way ChatGPT is doing tasks for us. Like you put a test, you give it an instruction, it processes it, and it brings out an output. Now we have gotten to that stage with robots, such that from the cameras that they have, they're able to see, and you give them instructions, and instantly robots are now able to automatically do that. And that is the current state of the art that we have within the past 2, 3, 4 years. And this is the traditional robotics. This is the classical robotics where you give a goal. Usually, when you give that goal to a robot, it's usually going to be some numbers, whether in the Cartesian space or what space or whatever how you like it. You give it in a goal in a language, usually with some numbers that the robot is going to understand. And the robot is going to use this planner, which means there's going to be some motion planning, trajectory planning, and while doing that, robot is also going to make use of some sensors in order to get feedback from the environment and pass this planning that it has done. Like, okay, this is how I want to do this activity to the controller. That is the actuation. So these are different systems, these are different blocks. What physical AI, embodied AI, robot learning has brought is that this goal, it has allowed you to be able to define it as language instructions, which means I can tell my robot that pick up this blue block or blue cube and put it at the edge of the table. Pick up this pen and put it in the pen holder. Those kind of language instructions we can give robots now. And robot is going to use its LLM to process that instruction. And instead of using the traditional computer vision algorithms that we may use, now we have VLAs also that are able to understand the scene of the robot, the environment of the robot. When it understands this environment, with the combination of that environment and the LLM instruction, The LLM instruction allows you to plan. Okay, this is how I want to get it done. The LLM allows you to see its environment and plan based on it also. Now, instead of having the traditional controllers again, we now have what we call action models. This action model also is also a transformer like the LLMs or the VLMs. People use different techniques. We have people that use diffusion transformers and different kind of things. Just like we have diffusion models in vision, we now have diffusion transformers also in robotics, and people use it. Action model can be different kind of things, and which we are going to talk about shortly. The question now we ask ourselves is, this is AI, this is machine learning, this is robot learning. For it to happen, how is it happening? It means we need a large amount of data. In order to do that, the very first or the largest data set that robots are using in order to do this kind of activity is the web data and human video. So which means all videos from Wikipedia, from YouTube, from Reddit, and test data from all these kind of sources that are open, all them, and we use this data in order to train the robots. But this data is usually not enough. It lacks the realism of a robot embodied data. Let's assume we have a 6 degree of freedom robot. Usually, the kind of data we want to see is that data that resembles what a robot will understand. Okay, these are the joint angles, these are the actuator angles, these are the gripper angles, and those kind of things. But the web data and the human videos data can teach robots some other things, but it lacks the realism that we actually need. It doesn't mean it is not useful. It is particularly useful for our planning stage and for the LLM. Okay, but the other category of data that is needed is synthetic data, and I'm going to tell us why we need synthetic data. Usually because we could actually collect robots data, which means I make my robots to do a lot of that activities or different kind of activities across different spectrum in different environments, and I capture this data. But there is a limit to the amount of data that my robots can be able to capture in a day, which means in a 24-hour window, one robot can only capture 24 hours of data, which is actually very small compared to the scale of the web data. So that is why we augment with what we call synthetic data, such that you generate simulation data using a very high compute resource in order to do that. And the challenge with synthetic data too is the embodiment gap. Some behaviors may be very difficult to simulate, to generate synthetically. Let's assume you want your robot to stand up from a fall. How do you make it stand up from a fall through simulation synthetically, and it resembles how it is going to do it in actual real life? So there's that gap too. There are some work that are bridging this gap. A lot of work is being done with NVIDIA. We have the NVIDIA Growth Mimic. We have USD, and we have this kind of things. We have the World Labs by Dr. Fifile from Stanford University, where they are providing platforms in order to generate synthetic data that close this gap. But again, there's still a little bit of challenge in that area. And the real world data is where you put your robots in different environments and you capture this data and you eventually use it to train. Challenge is diverse behavior may be limited. For example, when we have robots in manufacturing, maybe that robot is doing pick and place, material handling task, or palletizing. It knows how to do palletizing so well, but you ask it to paint, it may not be able to paint, which means I need to go into another plant where they are doing painting in order for that robot to be able to do it. Then, if I want that robot to weld tomorrow again, I need to go. So the diverse behavior is very challenging, and the environment. So that is why you augment real world data with synthetic data in different environments so that your robots can be able to operate and in this kind of environment. So what are the two major approaches that is being used in robot learning? The two major approaches is imitation learning and and reinforcement learning. Reinforcement learning, both are not new, but maybe the approaches that are being used in both fields are relatively new. What I'm trying to say in this case is that in imitation learning, basically you teleoperate your robots and you try to learn that behavior, and you assume that, okay, based on this imitation, your robot now should be able to do it because you have trained it on that particular task when I asked it to do something. So you teach a robot to perform those tasks and you leave it to do it. It will imitate that your behavior. So, which means you need to collect a teleoperation data. But reinforcement learning is a bit different, which means that we are rewarding the robot as it is doing it. And the robot is now going to generate some policy that allows it to do it. When it does it very well, you reward it. And if it doesn't do it well, you penalize it again. So that reward mechanism is happening with reinforcement learning. These are the two approaches that are being used. A lot of what I will be showing later is going to be discussing some state-of-the-art algorithms that talk about imitation learning. And we also have some other work, for example, from physical intelligence that combines reinforcement learning with imitation learning so that you take the advantage of imitation learning, the advantage you get from reinforcement learning, and you combine it into a VLA algorithm. So let's get started on that. This is where we have LLM. Within an LLM, what is inside it is transformers, stacks of encoders and decoders. But this video doesn't want to teach us what is a transformer and those kind of things. We can refer to some other videos on that. But what we do know is that we give it a text about, okay, what is a transformer? And your LLM, ChatGPT or whatever that we use, is going to now give us an output of another text. That is what we are. That was the beginning. And it all began from this: attention is all you need paper from Google. Then we begin to move towards multimodal, where instead of using text alone now, you can supply a text and image and videos. And the VLM can output text, it can output images and videos. And that is what we are seeing now in a lot of AI agents, a lot of GPTs that we have these days. They are basically multimodal in nature. They can give you images, they can interpret images, they can give videos and those kind of. So which means for a VLM to be trained, you need text inputs and you need images. Images and videos, they are just Siamese strings. They are brothers and sisters. So now with VLA, what is happening to is still that same old transformer, except that maybe the transformer can be shaped in different way. We are now adding what we call the robot observation data to your text and images. The robot observation data in this case is going to be joint angles of the robots. How the robot picks. How does it pick? What are the joint angles? And those are the most important observation data that you capture for that robot. And the robot in return is going to give us output that is going to allow it to control the robots and move those joints to a particular task. So I'm also going to give it tests. So tests can be pick up the blue block, and using the camera, the robot is going to know where the blue block is. What is the blue block out of all these blocks that I have? Go there to pick and do it. So a VLA builds on top VLM, VLMs build on top LLMs. All of them, basic unit that you have inside them are transformers. Transformers are stacks of encoders and decoders that relate together. Okay, and that is that and that. Like I said, encoders and decoders, but we're not going into the details of LLMs. What we do know is that for your tests that you input to your transformers, to your LLMs, for it to be interpreted, those tests need to be encoded. They need to be turned into tokens. So I'm going to be talking about encoded inputs a lot of time, test tokens. So those are the numbers that needs to be turned. So which means images too eventually need to be turned into what? they need to be turned into image tokens. The observation data from the robots will also eventually need to be turned into what? Test into robot tokens, robot observation data tokens. So basically, that is just the basic idea I want us to understand. And in return, it's also going to output some numbers, which are usually probabilities that you can add some classifier depending on what you want it to do. At the output, you can add a classifier, you can add anything you like, and it's going to give you what you need. So like I said, VLMs also image. So you need a transformer that is going to encode the image before it goes into the transformer, and you have your output. For the VLA, what you are going to be adding, this is just one example of how the VLA looks like. You still have your old VLMs, except that once it outputs some tokens, those tokens eventually are going to be these are going to be the latent representation of the images, of the observation, and of the instructions too. And once these latent representations are now going to become the inputs to your action experts, that is going to generate the controller inputs that are going to control the joints of your robots now, and that allows the robot to do whatever action you want it to do. And these are just examples of some videos. So this is from Physical AI, and you can see these are some robots that are folding clothes, and these are using I believe Pi 0.5, and these are VLA models, and you can see robot is trying to serve some coffee, and these are some examples that are being done currently. And also this is a company, Sunday Robotics, and I believe they also use VLAs. This is not a simulation, as they made us understand, and we can see what is happening currently now. And I think this video is also from Physical Intelligence, and robot is trying to arrange some eggs or something like that. So what are the different VLA models we have? Vision language actions. So what are the different models we have? We have single system VLA, which is going to be some giant neural network, some giant transformer. Give it your inputs, the robot's data, the text, which is the instructions, the images, which is the scene, the environment, and it is going to give you an output of the control actions that is going to control the robot joints. Those are one. Then we have the draw systems, which means at the beginning you are going to have a VLM, then you are going to have an action expert. So that's like two different transformers connected together. Then we have the hierarchical VLA systems. They resemble the dual system, except that you have an high-level planner that is going to, let's assume you say, clean the room. Then the high-level planner is going to output something that, okay, for me to clean this room, I need to pick up the pen, I need to fold the clothes, and it's going to give those lower level instructions, and some other time it can just be 2D policies that is going to give. It all depends on the hierarchical model that we talk about, and is also going to give an output of the control actions. But there are a lot of research papers on single system VLA, a lot of papers on dual systems, and a lot of papers on hierarchical VLA systems. I'm just going to be going through some maybe some of the popular examples that we have, and in this video we have different monolithic systems. Of the popular ones are the RT series, which is Robotics Transformer series from Google, and we have the Open VLA. All of them have the same high-level system architecture. There's a very large VLM based single system, so that's a very large transformer that accepts the language instructions, the vision of the environment of the robots, and the robot states, and it is going to give us actions that is we are going to use to control the joint angles or the base of the robot. Okay, so now let us go through the RT series first. For the RT series, we want to look at RT1. In RT1, what we do have is that, first of all, it was not pre-trained or trained on internet scale data. What was used is robotics data and instructions. So there were 700 tasks and 130 demonstrations for each of these tasks in this RT1. Another thing that we do have is that each of those tasks were now labeled with test instructions. So let's assume a robot is picking up an apple, it should be labeled with pick up an apple, which means that during evaluation, if somebody says, okay, pick up an apple, now the robot should be able to pick it up, even though it may be at a different location or in a different environment, but now the robot should have that ability to pick up the apple because it has been pre-trained through imitation learning on how to pick up an apple. Okay, so a brief about it is that the action tokens that are going to be predicted are discretized. So what we mean by tokenization of the actions is that they are discretized into token IDs. So let's assume a robot has 7 joints. Each joint is going to be quantized into 256 bins. So, and a full action is going to be a sequence of those 7 tokens. So the transformer basically learns to predict this just like it predicts words. So that is what, so it predicts those tokens. It can only predict 256 of them at 256, and just like it predicts words. So that is what is being done on the robotics transformer. The architecture, it uses an efficient net, which is a vision vision-based AI model that allows it to understand images and vision. So which was pre-trained on ImageNet. And for the architecture to be able to understand text, there is also another film. So we can go through the paper to understand the details about this. But the short of it is that the output of this film-based efficient net algorithm or model is that it gives us a very large sequence of tokens that represents the text and the instructions now and the images. And we have a token learner that takes it from a high dimensional state to a lower dimensional bin. So we are basically reducing the size of the tokens with the token learner. More details about this, then the output of this is passed through to the transformer, and we have this. So it was pre-trained, and those are the things we have. It is a bit slow and it has jerky actions. So that is an observation about the RT1. Then for the RT2, it is a very large based VLM based VLA model. It is 55 billion parameters in total. So this is very, very big. So you can't even run it on a simple desktop with some GPU. No. It was trained on internet scale data. And for the RT2, the VLM is, we have 2 VLMs that are being used. We have the PAM-E and the PAL-X. So I'm going to talk a little bit about this later. We already understand the tokenization and the de-tokenization of the actions, so that the robot is going to be that is what the robot is going to be. That is what the robot is going to understand. Okay. Another observation about the RT2 is that it was co-fine-tuned. So what co-fine-tuning means is that when we fine-tune, that means after it has been pre-trained, when we fine-tune, we take most other models. What it does is that it is going to most other models, what they do is they just take robot demonstration data and they fine-tune it on it. So which means if I want my robot to be able to do chores, I'm going to take different actions of chores, cleaning the room, cleaning the kitchen, and opening the drawer, and those kind of things. Those robot demonstration data are going to be used. That is what is common. But what RT2, what they did is that they added internet scale data, the web data, the videos, and those things that are not robot demonstrations data. The idea behind this is that, remember, they are detokenizing. We have 256 bins of actions at the output of our model. so which are very similar to text. So in order to add more semantic meaning, add more context to this, they added internet web data, test data, and those kind of things, and so that we can be able to, they can be able to interpret it or to understand it better, or to make it have better performance. So it was co-fine-tuned. That is another thing that we have to learn about this. So now to go into the VLM that were used, we already understand that anytime we have images, they have to be tokenized. And when these images are tokenized for the RT2, they before they are even tokenized, they are divided into patches, and it's passed through the VIT, which is the vision transformer. But the model that we have here, the VLM that we have here, RT2 use two different ones. So which means when you talk about RT2, you can be talking about RT2 PALI-X or RT2 PAM-E. And what happens in the PALI-X, which is 3 billion parameters, is that we have a transformer encoder and transformer decoder. A lot of other things that we already understand is the tokenization process and the de-tokenization that happens at the output too. We already understand that. But for the PAM-E, PAM-E is a decoder-only transformer. This video is not trying to explain what happens inside the transformer and those kind of things. We can go into the particular papers in order to understand what is inside the PALI-X and the PAM-E. But what I do want us to know is that two different VLMs were used. We have the PALI-X and the PAM-E that were used, and the PALI-X is a transformer encoder followed by a transformer decoder. We can go see that in the paper, in the actual paper. Now let's talk about the Open VLA. The Open VLA is also a monolithic system. One thing about the Open VLA is that it is a smaller model. It is a smaller VLA compared to the RT2. And another thing is that it is open. So which means people can use it. Like the RT2 is closed. It is only if you work with Google research that you can be able to use it. But Open VLA is opened. You can use it. You can use it to run inference and stuff like that. Again, the same idea. We have, instead of using vision transformers, VIT, that they use this vision. They use these vision models here, Dino, V2, and Siglip, and it was passed through two different ones for the images, and the test instructions passed through Llama tokenizer, and we have our also another Llama here that also is a VLM, multimodal VLM, and the detokenization process happens. So those are one big difference between this altitude that you see is that it uses what we are using to tokenize and to understand the images are different, and for the text also they are different. They are not also using PAM-E or PALI-X, so yeah, they are using Llama 2. So those are some of the differences that we have. This Open VLA was trained on 970K robot demonstration of OpenX embodiment datasets. From that time till now, the dataset, the OpenX embodiment dataset, has continued to grow within the industry, and I believe it's about 2 million demonstration now. So, but it is also a smaller model, 7 billion parameter, and it achieved about 16% better performance than the RT2, despite the fact that it is a smaller model. So this is just that about OpenVLA model architecture. It is monolithic system. It also uses an action detokenizer. Okay, good. Now we want to move into other forms of monolithic system, which is dual systems. So dual systems too, like I discussed, they are also monolithic, except that we have a system one, an high level planner, and a lower level planner. So we have a VLM backbone that is going to understand the language and the vision, and through this it is going to give an output which is the latent space, the latent distribution of the language and the vision, which is passed through, which is then served as an input to the action expert. Depending on the model, the action expert can be using flow matching or diffusion transformer in order to give us continuous actions, not discrete actions like we have in OpenVLA or RT2. Again, the VLM backbone can be Polygamma, it can be even be PalyX, it can be PAM-E, anyone that is open or that we may use. Now, the two examples that we are going to explore in this video is Pi series, which is Pi 0, Pi 0.5, and Pi 0.6, and GROOT N1 from NVIDIA. So let us start with Pi 0. Pi 0 also, again, we have the vision transformers, we have the OpenX embodiment dataset, we have Pi dataset that they collected themselves, and we have the internet scale data, and we can see that they use SIGLEAP as SIGLEAP and Gamma. So that is what is being used in Pi 0. I think we've come across this SIGLEAP before over here. They are not using Dinovit, so now they are using SIGLEAP. We begin to understand the different, the little similarities and differences between some of this work. Again, we have an action expert, and using flow matching, they are able to predict continuous state of the actions that we can use to control our robots. And that is that on Pi 0. Pi 0 was improved a little bit. Okay, this is Polygamma that was used as a pre-trained VLM, and we have the image encoder, linear projection, the text inputs, which are now concatenated tokens. Usually, we have this linear projection so that the text inputs and the image tokens now are going to be in the dimensional states, so that before they are concatenated. That is what is happening here. And so we have the linear projection. Usually this text inputs is supposed to be something like text tokens, because that is what we have a concatenated token here. Okay, and we have text outputs here. Before the text outputs, we are going to have output probabilities. These probabilities, which are tokens again, are going to be converted into text. So these are VLM baseline that was used in Pi 0 from physical intelligence. Okay, now for Pi 0.5, we have the pre-training step and the post-training step. What is really happening is, in the pre-training step, is they only wanted to adapt the model to diverse the robotic task. This Pi 0.5, even though I have said that it is a dual system, at the same time, it is also very similar to hierarchical systems, because now we have, which we are going to see. But in short, it produces continuous action chunks via flow matching, and it is pre-trained on discretized actions and post-trained with action expert via flow matching. What we do say, I was explaining that it's very similar to hierarchy, and we can be able to see it during this post-training architecture that we see here. When you give it a command that clean the room, and it's going to first of all output a lower level command, which is maybe pick up the pillow, fold the clothes, and those kind of things, before they are now passed through to the action expert. The action expert is going to take inputs of the latent state distribution of the inputs now, which is going to be the text and the images of the environment, and even the previous robot state. So what is the previous value, the previous action data that the robot has, and through flow matching we have continuous actions that we are going to have for the Pi 0.5. So it was an improvement on Pi 0. It was an improvement on Pi 0, but they did not stop there. We now have Pi 0.6 star, which is actually a combination of imitation learning and reinforcement learning. Again, we already know that for VLMs, VLAs, it's multimodal. We are going to have robot demonstration data. We are going to have the vision, and we are going to have the language. We already know this part already, but we now have the VLM backbone here, which is also a smaller model of what we have here that also predicts the actions tokens. But when the robot wants to make a mistake, it is able to know that this robot is making a mistake, and through the reinforcement learning, an expert is going to come to intervene that, oh, this robot is making a mistake. Maybe he wants to pick an apple and it was picking something else, or it was unable to pick the apple or the cube. Now it is going to be rewarded and penalized, and all those kinds of things that happen in reinforcement learning. So we are going to just quickly talk about some of the details that happen with the Pi 0.6. So Pi 0.6 itself has it has a different architecture from Pi 0.5. Note Pi 0.6 doesn't use any reinforcement learning now. There's no we have a bigger gamma model. We can, if we just come here, we can see 2.6b, but now we have 4 billion, and the action expert is also bigger. I think for the Pi 0.5 is 300 million. Now it is 860 billion. A lot of other things are similar in terms of the discretized actions during the pre-training, and we have continuous actions through flow matching eventually during inference and evaluation. So that is Pi 0.6. But physical intelligence went further again by including making the VLA learn from experience. When the VLA learns from experience, we have a value function. The value function itself is also a smaller sized model of the VLM, but is not as big as 4 billion. It is able to, it's good to 0 and -1. So if it is very close to -1, it means that robot is making a mistake at that point, and it is going to be trained, which means if it's making a mistake, you don't want the robot to make a mistake, and there's going to be an human intervention, which is an expert intervention. All these data were collected. Stage function that we use to train the robot. So the point is that this value function is like a coach that continuously monitors a player, which is the robot now, such that when the player is doing well, the robot, the value function also is happy like the coach. But when it wants to make a mistake, the coach is there to quickly point out the error, to notice the error, and to take note of that data, intervene when necessary, and all these data are collected, and we can go through the details in the paper. But the main big idea I really wanted to share in that there's an advantage function that is passed through to the actual VLA that allows it to know which interventions, or sometimes we may think robots wants to make a mistake, and that mistake did not actually happen. The robot was eventually able to complete the task. Robot, maybe the coach is saying, oh, you are not supposed to play the football like this, but eventually the player played like that, and it resulted into a goal. That is a good one. For instance, we want to take note of those kind of data, whether we should accept it or not. So those are the kind of high level thinking that happens with the Pi 0.6 using recap and or reinforcement learning. And this is the advantage I was trying to describe over here. Then we have the GOOT N1. The GOOT N1 also very similar to the Pi 0.5 or the Pi 0, except that it doesn't use flow matching for the action expert. It uses a diffusion transformer. So we have, this is the diffusion transformer. We already know coding process, the action tokens, and the noising that happens. This is a VLM model for the system 2 that allows you to plan, and the system 1 actually allow us to execute the action. GOOT N1 is from NVIDIA. It's actually a very good model that you can also use, and it's even with the good N1, it is actually a good model that you can even use to do mimic, which means we can use to generate other robot demonstration data. So which means if I collect 10 samples of robots picking a cube or picking a pen or clearing the table, I can generate more synthetic data that are going to closely match those other ones. So it saves time. That is how to use GroupTime 1, and we can also use it for different data for humanoid, for robot arm, and different kind of stuff like that. So this is the model architecture, and we can see it uses an EGU2 VLM base. We have the test tokenizer. We already understand all these already. And the diffusion transformers work by introducing noise, and we try to learn the noise, and so that whenever you have other data, again, can be able to extract the original data itself and remove the noise. So introduce noise, learn what is a noise, so that when you have other data, you can now be able to remove the noise. So just a little bit different way, but they are very close together in terms of flow matching and diffusion. Okay. That is that on that. Now we want to talk about the hierarchical systems. There are several of them. We have the hamster. What I'm going to say about the hamster is that for the VLM output, it is 2D robot part, which is not enough for the action or for the robot to perform its action. Then we now go have a 3D policy. This 3D policy may look like an action expert, but it's not an action expert because it is not taking a latent distribution now. It is taking 2D robot path as an input and using this 2D robot path to generate actual actions by also taking in input of high quality teleop robot. And we also have other ones like iRobots, which is also another hierarchical system that also has an high level policy VLM that inputs a low level language command. This low level language command can be the sequence of steps that is needed to complete a particular action. For example, if you ask a robot to make a sandwich, then the high level policy is going to give output like, okay, I need to pick up the bread, I need to place the bread on the plate, then I need to, those steps that you need to make the sandwich. And from that low level language command, then we have the low level policy, which is a VLA in this case, that is going to output action in a way similar to Pi 0.5 from physical intelligence, but there are still some very bigger differences. Because Pi 0.5 now in this case is using an action expert, not a low level VLA policy. So there are big difference between. So we have a lot of frontier models. We have maybe if you start to list it, we have maybe 50, 100 of them that has been released within the past 2-3 years. But I just want to summarize, especially for developers, searchers that want to try out things. Some models are closed, which means you cannot experiment with them. You cannot download the model card from maybe Hugging Face. But some are opened. So which means if you want to experiment, you can use OpenVLA, you can use Pi 0, you can use Pi 0. I'm not sure about Pi 0.5. Yeah, you can also use Pi 0.5. I think this is a mistake. Pi 0.5 is also open. You can use Groot, you can use small VLA. I need to confirm this. Okay, and you can see the release date. So the most progress that we've seen on VLAs just started within the past less than 4 years ago. So a brief note about fine-tuning is that usually we have a base model and you are going to spend a lot of money. You use very large data and it takes maybe 2 weeks, 1 month to train. After that, you have a pre-trained language model. This pre-trained language model can be what can be made open that developers, researchers can now use, download from GitHub or from Hugging Face. And the examples are the small VLA, the growth, the Pi Zero, and you can train on single GPU. And sometimes you can also rent GPU on the internet, but within few hours you can be able to produce your result and have a fine-tuned model. So this is a way for developers, especially when you want to compare models and see their capabilities, or maybe you want to make modifications, or you want to do some hackathon, or you want to, there are different hackathons that happen these days. So those are the ways we can fine-tune. You do not necessarily need to be from scratch. You can fine-tune, you can make modification to whatever you are fine-tuning. So how can we now make these models and make robotics and robots generally accessible for developers? There is the work from Lee Robot. I do not work for Lee Robot, but they are doing fantastic work in the area of making people purchase these robots. Usually about $200 to $300. You can purchase you can print it. It is open source. You print it, you buy the motors, and you buy all these controllers and connect it to your laptop, collect your teleoperating data, and can be able to use the robots in order to test out some of these algorithms that are opened and make modifications on them. So the process is buy or 3D print. You can just buy directly. If you want to 3D print, you can 3D print. Then you configure your motors, you collect all your operating data, and you train a policy to teach robots by fine-tuning, and you see your robots in action. So when you teleoperate, you are going to have a leader and a follower. The leader is going to be, it's just like you holding a joystick or using your keyboard or using a VR device. But in this case, you are using another robot to teleoperate another robot. Just collect this data of picking up pen in this. For example, this is small VLA that was done, and we can see now that in this work, it has been able to learn how to pick the pen, different locations, how to pick the cubes also at different location. So this was small VLA, and yeah. Now we can see now that I'm not using the leader again, because after training, I collected 50 demonstrations. The robot has now learned how to pick them up and put them in the bin. The challenge that we do have with VLA models currently is that the teleoperating data are not is not something that we can share and be able to use to reproduce the result. So for example, the cameras needs to be at their specific location that data were collected. So if there is a little difference in change in the location of the camera, for instance, then the robot is not going to be able to pick up these items. So this is one challenge I've seen working and trying to train VLA models and use them with the robots. But maybe you need to collect more data, because yeah, maybe I'm not sure, but that is based on my own work that I've collected 50 to 100 data and samples, and I try to do it. So usually sometimes I have to recollect maybe when the position of my cameras have changed. So that is one challenge with that. Okay. We can join the NVIDIA Robotics Discord community. There are a lot of resources that are being shared there. We can see other developers working on these kind of topics, and you can ask questions. Lee Robot also has a Discord community that we can join. So this is just my own motivation, my own interest in sharing this knowledge or giving a background on how these kind of models work. The references to the papers that are going to be in the link description below, and you can go through them in order to understand in greater details or in deeper details how these models work. My idea behind this video is just to give an high level understanding without going into the mathematics or those kind of details. So it's more like a literature review, yeah, of what VLA is and how to use them and how to get started with them. Okay, thank you. If you have any questions, let me know and I'll be happy to answer.